Proposition 3.7. The enunciation reads this: if on the diameter of a circle, a point be taken, which is not the center of the circle, and from the point straight lines fall upon the circle, that will be greatest on which the center is. The remainder of the same diameter will be least, and of the rest, the nearer to the straight line through the center is always greater than the more remote. And only two equal straight lines will fall from the point on the circle, one on each side of the least straight line. Okay, so this proposition is proving two different things, but here's what we're given. We're given the circle, ABCD. We're given diameter AD through the center. We're given center E, and we're given F, which is on the diameter, not the center. We're given a lot of things. Okay. So the line along the diameter that passes through the center, that would be from F to A, is the longest, and the remainder of the diameter is the least. And then the closer you get to AF, the longer you are. So actually I need to draw those in. Drawing BF, CF, and GF. Okay, so the one that's closest to AF is the next longest, then the one that's up next to that is the next longest, the one that's next to that is the next longest, until you get to DF. So the way that we'll write that is this. The thing that I'm trying to prove is AF is bigger than the next one, BF is the next biggest, CF is the next biggest, GF is the next biggest, and out of those, DF is the smallest. That's the first thing I'm trying to prove. And then the second thing that I'm trying to prove is that there's only one line, let's just say GF, there's only one other line from F that's the same distance as it from F. Okay, so that's the part two. So only one and only line, one line from F, one other line from F, that equals GF. Okay, so that's a lot of things to prove, but here we go. So our first statement is that we are going to connect all of these to the center. All right, so first statement is B to E, C to E, and G to E. That's from postulate 1, which says that we can connect a straight line from any point to any point. Okay. And so then we are going to say this. We're going to say that EF plus BE is greater than BF. Okay. And that's from the proposition that says in a triangle, so we're looking at triangle BEF, if you take two sides and add them together, they're bigger than the third side. Any two sides taken together are bigger than the third side. And that is proposition 19 from book 1. Nope, proposition 20 from book 1. Okay, so book 1, proposition 20. And so from there, I'm going to say that AE is equal to BE, and that's definition 15 and 16 from book 1, which just says radii are from the center and all the same as one another. And then I could do the long drawn out way, but basically he just swaps AE for BE in here, and he says that EF plus BE is greater than BF. And that's some kind of clever gymnastics using common notion 1-ish. We call it common notion 1.1. Okay, so again, since AE and BE are the same, oops, I wrote the same thing. We'll say EF plus AE. Okay, so this plus this are bigger than this. Well, EF plus AE are the same as AF, so EF plus AE are the same as AF. So this is the same as saying AF is greater than BF. So the way that I'm going to say that is EF and AE are the same as AF, which is common notion 4, which says that things which coincide with one another equal one another. Okay, so there's the first thing I was trying to prove, that AF is bigger than BF. All right, next thing I'm going to try to prove is that BF is bigger than CF. And so the way that he does that is he pulls out these two triangles right here. He pulls out BEF, or we'll pull out BEF. And we'll pull out CEF. All right. So in BEF and CEF, I've got BE and CE that equal one another. That's because they're radii of the same circle. I've got EF is common between them because it's the same line. And then I have BEF is bigger than CEF. So this angle is bigger than this angle. I'll try to write all that. So BE equals CE. I've got EF is the same. And then I've got BEF, angle BEF, is bigger than angle CEF. Oops. CEF. So this is definition 15 and 16. This is common notion 4. Oops, common notion. Yeah, 4. Things which coincide equal one another. And then BEF is greater than CEF would be the whole is greater than the part, which is common notion 5. And so because of these, I have what's called side angle side, but side angle side inequality, where I have two sides equal to two sides respectively, and the included angle in one is bigger than the included angle in another. And what that means is that with side angle side inequality, the side that we haven't discussed yet in this triangle is bigger than the side that we haven't discussed in this triangle. So all of that set up, we can now say that BF is bigger than CF, and that is because of proposition 24 in book 1, which says basically that. If you have two sides equal to two sides respectively, the angle between them, one's bigger than the other, then the greater sides across from the greater angle in that triangle. All right, good. So BF's bigger than CF. And of course, because he's awesome, he says that similarly it can be shown that CF's bigger than GF. Okay, CF's bigger than GF. And that is similarly. Could do all the same stuff, but we won't. Okay. All right, and then we have, from there, what we have left is to show that GF is equal to FD. Okay? All right, so he's going to do this the same way as he did the earlier one, and he's going to use triangle GFE now. And so in that, we'll use GF plus FE is greater than EG. And that's from proposition 20. Okay. And so, and in those I've got GE, and I'm going to use DE now. And so EG is equal to ED. That's definition 15 again. From book 1. Okay. And so then I'll just swap these guys and do GF plus FE is greater than ED. And that's again, common notion 1.1. All right. So I'm just exchanging an EG for an ED. All right. So I have GF plus FE is bigger than ED. And I will subtract FE out of both of those. And so if I take ED and take out FE, then what I'm left with is FD. And if I take GF plus FE and I take out FE, then I'm left with the GF. So I'm left with GF is bigger than FD. Okay, so again, that's common notion 4 like above. And then if I subtract equals from equals, I guess this is a little bit different. It's common notion 2, but since it's unequals, I call it common notion 2.1. All right, so I've got GF is bigger than DF or FD. So I've got the first part done. Call that 12 and 13. Okay, so that one is done. Okay, so now for part 2. Start back over. Out of space. Whiteboard's really warped. It's all the sounds of bending metal. All right. So I'm on to statement 14 now. I'm going to try to show this, that there's only one other line from F that is the same length as a given line, and we're going to call that, the given line GF. Okay. So the way I'm going to do this is I'm going to make an angle. And it's going to be F, we're going to say H over here. I'm going to make angle HFD equal to angle GFD. All right, so HFD is equal to GFD. So I'm going to make that angle the same measure as that angle. And I'm going to use proposition 23 from book 1, which says from a given line, so that's line FD, and a given point on the line, that's point F, and if I have a given angle, so that's angle GFD, off of that given line, from that given point, I can make an angle equal to the given angle. So, there we go. All right, so those two angles are equal. All right, I'll connect EH, okay, so E to H, that's postulate 1, getting close here. All right, so from postulate 1, then I've got these two triangles. I've got EFG and EFH. And for time's sake, we'll just mark these. EFG, we won't write the steps, EFH. But I know that EF is common to both. I know that EG and EH are equal to one another since E is the center. And I know that these two angles are the same because I just made them equal. And so I have side angle side equality. And so what I can conclude is all the remaining sides are equal, but the one that I care about is that GF is equal to HF. So I did make one that's equal, and that would be from proposition 4, side angle side from book 1. Okay, and so I've got one length that's the same as GF that is kind of the mirror image on the other side. And so I'm going to show that's the only one. And so I'm going to assume that there's another one somewhere in the circle. And I'm going to assume that it's over here. And we'll call that GFH. We'll call that J. Okay. So I'm going to assume that JF, missed. I'm going to assume that JF is equal to GF. That's my assumptions, that's 17. I'm going to try to say there's another line that's the same from F, that's the same length, okay? Well, here's the problem, if that's true, that there is another line. Well, I know that JF has to be bigger than HF because that was 3.7, the one I'm proving, part 1, says the closer I get to this little length, the smaller the lines get. So this one's smaller than this one, which is smaller than this one. Okay, so JF is bigger than HF. And since I know from earlier that HF and GF are equal, then I've got, if JF is bigger than HF, then JF also has to be bigger than GF. Okay, so because GF and HF are equal, then if JF is bigger than HF, JF also has to be bigger than GF. And that would be combination 1 with inequalities, so we call it 1.1. So I have these two things right here. JF is equal to GF, and JF is bigger than GF, and those two can't be true at the same time, so I have a contradiction. And so what that means that I have a contradiction is something that I have on the board is false, and the only thing that I have that could be false is my assumption. So JF cannot be bigger than GF. JF cannot be bigger than equal to GF. Okay, and which means that there's only one line. I could do the same thing no matter where I put this point, on this side of H or on that side of H, up or above the diameter. And so what that means is that there's only one line from F that's equal to GF. So that's the end, Q, E,